Now, the main difference between an arithmetic sequence and a geometric sequence is that instead of being added or subtracted from term to term, as I was describing in the last video, where an arithmetic sequence always has a common difference, like it's growing either by 2, the same amount each term to term, in an additive sense, or it's being subtracted negative 19, negative 19, negative 19. And basically, adding and subtracting are both called additive because you could add a positive number or add a negative number, and basically each term has a common difference, whether it be positive or negative. So the key difference between geometric sequences is that it's not being added or subtracted, it's being multiplied or divided. So from term to term by term, as you're seeing the growth, like in this particular example, the first term, well, the difference between those is 3. The difference between the next one is not the same. So this one is not arithmetic because it's not growing by 3 each time. But here, if we look at it on the multiplicative scale, from the first to the second, it's being multiplied by 2. And then multiplying by 2 again and again. Or in this case, you could say each term is being doubled. It's doubling, and this is an idea of a geometric sequence where we refer to the multiplier from term to term as the common ratio within the sequence. And also, kind of like I was saying, you could find the difference above by subtracting any two terms. Here we could find the common ratio by dividing each term, right? And that's what a ratio means, is the division. If I took a2 divided by a1, 6 divided by 3 would give me 2. That's why it's called the common ratio. But anyways, if we look at the definition, it will be in alignment with exactly what I just said. But it says a geometric sequence is a sequence of the form a times r squared, a times r, a times r to the fourth. And there's probably a pirate joke in there based on all the r's, but I digress. And what it says is the number a is the first term, it says r is the common ratio, and the nth term of a geometric sequence is given by this formula. So it's very similar to in the last video where I talked about the formula for an arithmetic sequence. For a geometric sequence, it's very much the same. The only difference is the first term, we're still going to call that a. So looking at this example here of 3, 6, 12, 24, a, our first term, is going to be 3 in the same sort of way. And r is always the common ratio. That is basically what is being multiplied from term to term. So like before, here, instead of being adding by 2, here we're multiplying by 2 because each term is double the previous. And notice how that makes sense based on this expression. It says that a geometric sequence is of the form a, first term, and the second term is a times r. So 3 times 2 would be what's next. Kind of like, well, that's exactly what's happening, right? I'm going to go 3 times 2 to get to 6. Then I would be 6 times 2 to get to 12. And that's why, well, the third term would be 12. It's quadruple the first, right? Because I doubled it and then I doubled it again to get to 12. And then if I double it again, that would be 3 times 2 times 2 times 2. Each term has another consecutive r within it. And the recursive formula for a geometric series, instead of being an minus 1 plus 2, like it was for the arithmetic, it would be an minus 1 times 2. Otherwise, exactly the same idea. But basically what you might be noticing is this is what gives, instead of being a linear function as it were with an arithmetic sequence, a geometric sequence is an exponential function. It's growing exponentially by a factor of 2, meaning that its base is 2. And if we look at the general formula, this is exactly what will happen. And like I did before, if we start plugging in a1, a2, and a3 into this general formula, we'll see why this makes sense for modeling a geometric sequence. So like here, if I plug in a1, I would have a times r to the 1 minus 1 power, and that's, of course, a times r to the 0. And anything to the 0 power makes 1. So this would leave me with a times 1, and a times 1 is, of course, a. And so basically, I would start with the first term. And if you remember back to, when we talked about exponential functions like pe to the rx power, the general growth formula, kind of like mx plus b for a line, the p is the starting value, the principal value of an exponential growth, which notice in this formula is out front. A is the first term. This should make sense. And instead of being the base of this growth function is always r, the common ratio, because that's always what we're multiplying by to get the growth. So that's kind of like taking the place of e to the r, which is the representative growth rate of the function. And x is like my input. And instead of just being x, it's n. Instead of being n, it's n minus 1 for much the same reason as the last time when I was talking about arithmetic sequences, but that's because we want the first term to just be a, and that we want it to be 0. So the first term produces 0. That's why we have not just n, but n minus 1. That will ensure that it starts at a. And then when I look at a2, that would be a times r to the 2 minus 1 power by plugging that into the formula. And that would give me ar to the first power. And that's exactly what I want to have happen. I want to take the first term and multiply by 2 in the case of the other one. But, you know, the next term should be r times greater than the first. And then the third term would be a r 3 minus 1, which would be a times r, or ar squared. And, you know, each term will be bigger by a factor of r, which is the goal. So again, summarizing, this general formula will give us the formula for any geometric sequence. And again, if we can recognize it to be geometric by looking at, is it being multiplied or divided by the same thing each time, then we can always use this formula to write its formula. Again, formula for the formula. So, you know, if in this case we wanted to write a formula for this geometric sequence, we could start with the shell. So it should be a, which we know to be 3 in this case, multiplied by r to the n minus 1 power. And I'm just going to put it in parentheses because a and r are implied to be multiplied together. But, you know, if I don't write this, I could also write a little time symbol in between them as well. But I think it's more clear if I put in parentheses. But basically only r is raised to the n minus 1, not a, as it means in that expression. And this would give us our formula. And as I said before, if we wanted to make sure, how do I know that this formula works for this particular sequence, we could always start plugging things in to make sure. So if we start with a1, I could see, okay, does that work? This would be 3 times 2 to the 1 minus 1 would be 0. And 3 times 2 to 0 is 1, so 3 times 1 is 3. That's good. Then I could check a2, that's 3 times 2 to the 2 minus 1 is 1. That's just 3 times 2, that's 6. And a3 is going to be 3 times 2 to the square, which is 3 times 4, 12. And this pattern is exactly what I had. So we know we're good to go. On the second page of the packet, I gave a bunch of practice questions for determining it, but let's look at just one more. Because, you know, an arithmetic sequence could, instead of being multiplied, it could also be divided. So, like looking at example number 2 on the next page, it says let a sub n be equal to 24 times 1/2 to the n minus 1. So notice this is in the generic format for a geometric series, but the common ratio doesn't, instead of being multiplied by 2, it could also be divided by 2. It could be shrinking instead of growing, just like how it could be added or subtracted with an arithmetic sequence. But if we wanted to list the first 6 terms, that would just be a matter of plugging in 1, 2, 3, 4, 5, and 6. But it's a little bit easier to do this once you see the pattern. But formulaically speaking, I could start with a sub 1. That would be 24 times 1/2 to the n minus 1, which would be 0. And anything to the 0 is 1, so this would just be 24. And again, the first term should always be out here if it has the proper structure. Based on the formula. So then the second term would be 24 times 1/2 to the 2 minus 1, which is 1. So 24 times 1/2, well, that's just half of 24 is 12. And basically, since the common ratio is 1/2, that just means each term will be shrinking by half, or being cut in half. Again, an exponential growth function, which we often call exponential decay. You know, and so then the next one would be cut in half again, be 6. And, you know, I'm just going to sort of take a shortcut here, but since each term is growing by half, once I figure out that pattern, I could just sort of do it recursively and say, well, each one is just going to be half of the previous. Then it would be 3/2, and then 3/4, and so on. But, you know, we could then analyze what happens as this sequence gets smaller and smaller and smaller. It's just going to be half, half,